Well, good day, everybody. This is Chris with the Ancient Scholar. I hope this video finds you all doing well. I'm back in the clinic. It's the middle of the night right now, and I have a few minutes of downtime. And so I thought what I'd do is do a video talking about something that is a bit unique and not as well known or encountered, but it's still very interesting, and I may end up doing more than one video if there is some interest in this topic. And this is on something called THAM. THAM is also referred to as tris-hydroxymethyl aminomethane, or THAM, THAM for short. What is THAM? THAM is essentially, it's an amino alcohol that has that amine group, which has a pair of electrons on it, and that pair of electrons acts as an acceptor for protons, and so it is a base. And so THAM is something that can be administered in lieu of sodium bicarbonate. So typically when we talk about treating severely acidotic states, sodium bicarbonate comes into the discussion. And this is a bit contentious because there are lots of considerations when thinking about sodium bicarbonate. First of all, typically we're talking about severely acidotic, metabolic acidosis in particular, severely acidotic people who are at high risk for problems with their heart, problems with their brain, problems clotting potentially, mainly the heart. The cardiovascular problems can get really pronounced and become profoundly acidotic. Your blood vessels don't constrict like they're supposed to. Your heart has a really hard time. You can go into cardiac arrest. It's really hard to resuscitate profoundly acidotic individuals. I'm talking pH of, less than 7, 6.9, 6.8. You kind of getting into that incompatible with life kinds of pH. I'm not talking about 7.2 or 7.3 pH. We're talking really severe metabolic acidosis states. And THAM is something that can be considered. And so if you've never heard about it, I thought I'd talk about it a little bit. So the first thing I'd like to talk about is just bicarbonate, sodium bicarbonate, because it's ubiquitous, it's cheap, and many of us know how to use it fairly well. And so when using bicarbonate for severe metabolic acidosis and other conditions like hyperkalemia, or sodium channel blocker toxicity, there are some other indications for sodium bicarbonate. What's happening at a physiological level? Well, to understand that, you kind of need to understand how carbon dioxide is transported in the body, or about 70% of the carbon dioxide that's produced in your body is transported this way. And that is in the form of hydrogen ions, hydronium ions, and bicarbonate ions. And so this is the basic formula here. So carbon dioxide is produced in your tissues, and then in the presence of enzymes, specifically carbonic anhydrase, that catalyze this chemical reaction, carbon dioxide chemically combines with water, H2O, to form something called H2CO3, or carbonic acid. And that carbonic acid is a weak acid, and so some portion of it will dissociate into hydrogen ions and bicarbonate ions. And these hydrogen ions and bicarbonate ions are charged. They can dissolve in your blood, and then in the lungs, in the presence of carbonic anhydrase that catalyzes this, the hydrogen ions and bicarbonate ions can recombine to form carbonic acid that then breaks down into water molecules and carbon dioxide gas that can be eliminated. So carbon dioxide gas comes in, it gets converted into something that can dissolve in your blood, and then it comes out as a gas on the other side. Now, for this to work, you notice that these arrows move. I've got one arrow moving in one direction and another arrow moving in another direction. So this is, in chemistry, we call this an equilibrium reaction. And that is to say that this reaction can move as easily, it's energetically as favorable to move in this direction as it is in this direction. Many chemical reactions are not equilibrium reactions, and they can only move in one direction, right? The energetics only favor a certain direction for a chemical reaction. Generally, the products come in and the energies within the chemical bonds are fairly high, or the reactants come in, there's a chemical reaction, and then you have products where the energies are lower, right? And so you have a release of energy, maybe in the form of heat, and you have an exothermic reaction, say, maybe this is like a combustion reaction. And then when when the bonds recombine in the products that are formed, right, those chemical bonds are at lower energy, and the reactants are higher energy. And that kind of chemical reaction is generally what we call irreversible. In order to get the products to form back into reactants, you'd have to pump a lot of energy into that system to get the chemical reaction to work in the opposite direction. That's not the case with something like this, which is an equilibrium reaction. And it's essentially just the law of what we call the law of mass action. So typically what happens is, if I dump a bunch of molecules in one end of this equation, it will shift the equation in a direction away from the molecules that you're dumping in. And generally speaking, in a normally functioning person, what's happening is the tissues are making carbon dioxide, so carbon dioxide spilling out into the bloodstream, and then you're breathing that carbon dioxide off, right? So CO2 is always being introduced as a reactant, and it's coming out, right? Carbonic acid is being formed as a product. And so the constant addition of carbon dioxide and the constant elimination of it on this other end favors the chemical reaction moving in this direction. All right, so you have a bunch of reactant that is being dumped in on this side that favors the products. It pushes the chemical reaction, right? There's more mass coming in on this side, and the law of mass action is going to push the chemical reaction in this direction, right? So what can happen when you administer sodium bicarbonate is the sodium bicarbonate can dissolve in your blood, and it will dissociate into sodium ions and bicarbonate ions. And the bicarbonate ions do functionally act as a base. They can accept protons, and they can buffer pH changes. But the problem is, when I introduce a bunch of sodium bicarbonate, that's introducing mass right here in this chemical equation, right? And if I have a bunch of mass that's being introduced here, that can shift the chemical equation back in this direction, right? And so what often happens is, when I administer sodium bicarbonate, that bicarbonate, right, so I'm adding a bunch of product essentially here, and that will shift the chemical reaction in this direction toward carbon dioxide, and you will often see the carbon dioxide level will increase. So you're functionally administering carbon dioxide to somebody when you administer sodium bicarbonate. Now, as long as they have a functional respiratory system, you can give the bicarbonate, and then they can just breathe that carbon dioxide off, and it will shift the chemical equation in this direction, and you can eliminate that volatile acid, the carbon dioxide. The problem is, what if you have a really sick patient who is in respiratory failure, right? Maybe this is someone who's septic and they're developing ARDS, they have that type 2 respiratory failure, and they're not able to effectively eliminate carbon dioxide, or there are some other things going on that are preventing them from, they're in cardiac arrest, and you don't have a good airway, and you're not perfusing the lungs very well, or you're in a profound shock state with poor perfusion to the lungs, things like that. In that case, you may be well motivated administering sodium bicarbonate, thinking that you might be treating an underlying metabolic acidosis, but because you can't eliminate that carbon dioxide, now you have paradoxically increased the CO2 and potentially have caused additional problems with the pH that you were trying to fix. So that's kind of one of the major issues that we run into with bicarbonate. And yeah, there's, you add some sodium and maybe hypernatremia, but that's a primary issue is this carbon dioxide. Sodium bicarbonate is functionally a vial of CO2 that you're adding to somebody. So that's right. We all should know that or understand that. So let's talk a little bit about THAM. So when we look at THAM, so again, THAM is tris-hydroxymethyl aminomethane. So what does that actually mean? So this is what a molecule of THAM looks like right here. So I've got these 3 carbons here in the middle, and I've got these 3 hydroxyl or these alcohol groups. And then attached down here, I have this NH2 here group, right? I've got this amine, and there is a pair of electrons on that nitrogen, and those pair of electrons attract protons, and that's essentially what makes this a base. It attracts or it accepts protons. And so there are basically 2 physiological mechanisms for how THAM works. So the first mechanism is R just means everything else in chemistry, right? So what I'm really interested in is this NH2 group here with a pair of electrons, and then the R is all the rest of this stuff here. So this is my molecule of THAM. And so if somebody has a lot of carbon dioxide in their blood, I can administer THAM, and THAM will, carbon dioxide plus water, okay, so CO2 plus H2O will yield H2CO3, and then you'll have hydrogen ions, and you can have this R here, this R NH then can bind to the carbonic acid that's being produced, and you will have those protons that are being released from the carbonic acid combining with the THAM here. So instead of NH2, you have NH3 plus, because you now have a proton that is associated with that NH2, that amine group there. And then you will also have that bicarbonate left over, all right? And then the other way is pretty straightforward. It can directly bind to hydrogen ions that are released from other acids, right? It doesn't have to be carbon dioxide, but it can be carbon dioxide. But in either case, the chemical reaction really only moves in one direction. And the interesting thing about THAM is you can administer THAM and it will actually decrease carbon dioxide levels versus bicarbonate, where you administer sodium bicarbonate and it will increase carbon dioxide levels. So THAM might actually be a reasonable option to administer in patients where the respiratory status of the individual is not as robust, right? They're they have ARDS. Maybe this is a cardiac arrest, a code that you're working. They're really acidotic. You're not sure how well you're circulating, perfusing the lungs, and you would rather not increase their carbon dioxide levels. Maybe giving THAM might actually decrease the carbon dioxide levels and also buffer some of the metabolic acidosis that's being produced. So that's kind of the basic motivation for why THAM may be a helpful agent in certain situations. If you all are interested in THAM, I could perhaps talk about it in some more detail as far as indications, possible contraindications. It's not like there's a robust amount of data out there on THAM. There is some, and there was actually a fairly recent podcast that covered this. The EMCrit podcast covered this, and they talk about it in a little more detail than I am in this particular video, but I figured at least I would give you kind of the basic physiological motivation for why THAM might be an option in certain patients. So hopefully you all found this video helpful, and yeah, as always, take care, and we'll see you in the next video.